All right, if you're interested in how to calculate these onion layers or these hollow spheres, problem number 110 shows you the formula for that. Actually, if you've taken calculus, then it's pretty easy to do. But if you haven't, you still can do it. But you don't need to do this. You just have to understand that as you get further from the nucleus, as R grows, the volume of the sphere grows here. It's nonlinear. So this is number 110. Now, well, why? Let's go back to this. Why did the Bohr model fail? The Bohr model failed basically because of this. If the 2s and the 2p and the 3s, 3p, and 3d all stayed the same energy, then we wouldn't have known Bohr model was wrong. The reason you know the Bohr model is wrong is because of this failure. That is, what happens in a multi-electron atom is that the 2s and the 2p are no longer the same energy. And you might go, why are the 2s and the 2p no longer the same energy? Did the effective distance change? No. The effective distance stayed the same. So what changed? What changed is their penetrating ability, because penetration makes a difference when there's something else present. Shielding. With a one electron species, what I mean by shielding is in a one electron species, there's only one electron. And so that one electron is going to see the full nuclear charge, which is going to be Z. But when we have multi-electron species, what happens is that if I look at a 2s electron, there's probably a 1s electron there, or two of them. If I have two 1s electrons here, that's blocking or shielding some of the nuclear charge Z from this one. And so there's another effective, it's called Z effective. How much of the nuclear charge does that electron see? And so what we have is this. When we're looking at multi-electron, we have to factor in the interaction of the other electrons with the electron in the tube. And so right now, if I look at these two orbitals have the same energy, correct? But all of a sudden, if I put 1s electrons in there, well, let's do that. I'm going to put some 1s electrons in here. Actually, let's go with a different color. Here. If I put some 1s electrons in there, the 1s electrons are going to occupy this volume here. And so now I got the 1s electrons in here. I got the 1s electrons in there, then the 2p and the 2s they want to see the nuclear charge here. The nuclear charge is here, but the 1s electrons are shielding or blocking the nuclear charge. You know, because electrons are negative, nucleus is positive, that's a favorable interaction. And so now I got these 1s electrons shielding the 2s and the 2p. Even though the 2s and the 2p have the same effective distance, they have different penetrating abilities. That is, if I have a 1s electron here, the 2s electron can sneak in to this volume here, right? And so let's say the electron, in one instant of time, the 1s electron were here. Well, that means the 2s electron might be here. That means the 2s electron sees the nuclear charge here. And so this is what we call shielding. When we have the 1s electrons here, all of a sudden the 2s and the 2p are no longer going to be the same energy, even though they have the same effective distance. The reason is because they have different penetrating abilities. The 2s are much more penetrating. Since the 2s are much more penetrating, they're going to be lower in energy than the 2p. The 2p are less penetrating. And so we break this down into what's called Z effective. How much of the nuclear charge does that electron actually see? And this is going to hold. So the same thing here. The 3s are more penetrating than the 3p. The 3p are more penetrating than the 3d. We can see that easily in the RDF. When we go back to the RDF, take a look at that. Look, the 3s are more penetrating than the 3p. The 3p are more penetrating than 3d. So even though these three orbitals have the same effective distance, this one is much more penetrating and less susceptible to shielding. And so if I had the 1s electrons blocking here and the 2s electrons blocking here, the 3s might sneak in closer to the nucleus and become lower in energy. The closer it gets to the nucleus, the lower in energy it is. Whereas the 3p are less effective and the 3d aren't very effective at all. The 3d, in other words, the 3d are very effectively shielded by inner electrons. And so this is the result here. The result is that in hydrogen atom in one electron species, the energy only depends on N. In multi-electron atoms, the energy depends on N and L. The higher the N, the higher the energy. The higher the L, the higher the energy. L's impact isn't as significant as N. N has a much greater impact on the energy than L. And so all of a sudden the spectrum gets a lot more complicated. Earlier the spectrum from the hydrogen atom, was okay, we got 3s going to 2s, that's the red line, so drop here. But now you have all these other levels. All these other levels and all these other potential transitions. And in fact, there's all kinds of restrictions on these transitions, because when we factor in the quantum mechanics says that these transitions can only occur, because angular momentum is like, what's a good way of talking about angular momentum? Have you heard the term angular momentum before? L is called the angular momentum quantum number. So angular momentum is if you have some momentum, whatever, you got some, it turns out that there's only certain transitions allowed. And so, for example, you can't, certain transitions are forbidden because of conservation of angular momentum, which is energy, this kind of thing, or there are things we call selection rules. And so not all these transitions are allowed. So, for example, we can have this transition, but we cannot have this transition. And all these things come about because of looking at the quantum physics of these. And so certain transitions are allowed, like delta L1 versus delta L0, and so those add up. And so the spectra become a lot more complicated. When we look at the spectra, let's look at spectrum. Okay. Well, actually, let's not use the books, spectra. They show helium, which is a little bit more complicated, but let's take a look at some others. Okay. There's lots and lots of these. But we see hydrogen here. There's more. They're showing additional lines. These are in the UV. You can't really see them, but the detector can see them, and so they aren't actually violet. These are the ones in the visible part of the spectrum here. But you see helium. Look at helium spectrum. Helium has 2 electrons, and so now all of a sudden we see the spectra become much more complicated. Neon. Look at the spectrum for that. Spectrum for that. Sodium's simple. These two, when you look at sodium street lamps, they look kind of yellow, orange. That's because of these 2 lines here. And that sodium lamp over there does the same thing. These are from a from a 3p to a 2s transition or something like that. Generates these lines. We have lines in the infrared. We have lines in the UV as well. There's a mercury here. And actually, these atomic spectra can be used to identify elements. So, for example, if you look at the solar spectrum, you'd see, the hydrogen lines missing out of the rainbow, and the helium lines missing out of the rainbow, this kind of stuff. And so, what these are often referred to as the atomic fingerprints for the elements. And so we could use these to identify elements, because when you look at the spectra, they're quite a bit different. Potassium, that's interesting. here, because that's showing, this is showing a continuum, isn't it? I don't know why that is. It must be potassium metal. I'd have to see why this is emitting, but that's unusual. Unless, for example, if it were a big chunk of metal, then it could emit black body like that. Then you see cadmium, lithium. So we could use these line spectra easily to identify. Not only can we identify, but we can tell how much is there by doing like a Beer's law type calibration, where we look at the intensity and we plot the intensity. We wouldn't look at spectra like this. We look at peaks, how big the peak is, that kind of stuff. Here's a continuous spectrum with an incandescent lamp, and this would be just tungsten metal. If we look at the spectrum for tungsten atom, if this is tungsten metal spectrum, what would tungsten atom spectrum look like? Would it also emit a rainbow of colors? No, it would look like this line. Why? Because the electron is confined to a much smaller box. The electron is confined to a very, very large box, and it's going to be pretty much continuous, etc. All right, so that's atomic spectra. And the atomic spectra is much more complicated than what the Bohr model predicts, because the energy level diagram is a lot more complicated than what the Bohr model predicts. Okay, plus our picture of the atom is quite a bit different as well. And so what we have to do is we have to be able to draw this, and we have to be able to draw this. And we have to be able to understand the difference in these. Well, one thing is, why is the 1s not the same energy? Why isn't the 1s the same energy? Yeah, it's got to have more protons. If we got more electrons, we're going to have more protons. That's it. Okay, so we want that. We covered this. See, I haven't covered this yet. Now, all right, so this would be like lithium. If I went to something like beryllium would be even lower. Boron, lower. As we add more protons, right? As more protons, Z grows. And it's just going to shrink the orbitals, but we're going to get a lot more electrons in there anyway. Now, what we're going to do next is we're going to fill the orbitals, these are orbitals, with electrons. And so when we fill the orbitals with electrons, we have to be aware of this, the spin of an electron. The spin of an electron is a quantum mechanical property. That is, electrons act like little bar magnets. They're going to have north pole and a south pole. And it turns out that there are only two spin orientations allowed. There's one that we call plus 1/2 here, shown here, and one that we call minus 1/2, shown here. And you don't have to know which pole is up or which pole's down or whatever the arrow. The arrow's pointing to the south pole here, which is fine. Usually we think the north pole's at the top, right? But it doesn't matter. We aren't going to worry about this so much. And so when we put these electrons in here, it turns out that there's something called the Pauli exclusion principle. Have you heard of the Pauli exclusion principle? There's all these names, Heisenberg, Schrodinger, de Broglie. And there's one more that you need to know for this chapter, and that's Pauli. And you need to know the Pauli exclusion principle. What is the Pauli exclusion principle? The Pauli exclusion principle is this. The first three quantum numbers tell us the address of the electron. That is, they tell us what orbital it is. And there's one more quantum number, S. This tells us the spin orientation, whether it's spin up, which we call like this with the arrow pointed up, or spin down, like this. Spin up gets +1/2, spin down gets -1/2. And so what we say in the Pauli exclusion principle is that no two electrons in an atom can have the same set of 4 quantum numbers. That would be a violation of the Pauli exclusion principle, not holds. So it comes from quantum. And so no two electrons in the same atom, can have the same set of 4 quantum numbers. And so this means that an orbital can hold a maximum of 2 electrons. One spin up and one spin down. Max capacity, 2 electrons. And so we can't put more than 2 electrons in an orbital because of the Pauli exclusion principle. We'll just take that as given. And so this is just showing the spin, but we don't really care. We just know we have an up arrow and a down arrow. That's it. You can tell, actually, you can tell that the electrons have a spin. This is a very, very famous experiment called the Stern-Gerlach experiment. This was done. The electron spin was a, you know what theories should do? What should theories do? Theories should predict. And so what Stern-Gerlach did was they predicted, based on quantum mechanics, they predicted that the electron's going to have a spin, and they set out to measure the electron spin. They predicted that the electron's going to have a spin, and the way they measured it is by shooting silver at them through here, through a magnet. And pretty much they got an even distribution. Some were spin up, some were spin down. And they interacted with the magnet this way, and they got 2 strikes here. And so some of the silvers were north pole, some of his over were south pole. That's it. And so this was a prediction, a successful prediction of quantum mechanics. You know, they hypothesized this, you could say, based on quantum mechanics, or just predicted this. There is another prediction from quantum mechanics, and that was that not only do electrons have spin, but nuclei have spin too. Nuclei. It's kind of a sad story. Did I tell you it? So these guys predicted that the nuclei have spin as well, and they set out to measure this, or to, you know, experimentally determine it, because they predicted that, you know, nuclei are going to have spin and they're going to be measurable. But they failed. And the reason they failed was because of the electronics. This was in the 1950s. Electronics, they had these big transistors and whatever else, and the amplifiers weren't strong enough. And then the 1960s comes along, and another group of physicists decided to give it a go again. And they decided, okay, we're going to measure nuclear spin. And they were successful. They were successful because of electronics. And then, well, this was a significant development because that led to, the MRI, magnetic resonance imaging, and nuclear magnetic resonance. So it was a very significant development. And so they were awarded the Nobel Prize. And who are they? Was it the original group that was awarded the Nobel Prize, the second group, or both groups? The second group. The first group was totally ignored from the Nobel Prize. So this is one of those stories that goes around because it's totally unfair, and everybody realized that it was kind of totally unfair to the original. It's just because of electronics. Okay, so when we fill the electrons, we can fill up the orbitals. There are different ways to fill up the orbitals. You know, to draw energy level diagrams takes up a lot of space. So what we do is we try to do this more compact. Ways to do it more compact is not to draw out the energy level diagram like that, but just to write it out as a line. But you lose information here. When you write it out as a line like this, do you see the gaps? No, you don't see the gap. So when we condense it like that, we're missing the gaps. We're missing, do you see if the electrons are spin up or spin down? No. So we lose a little bit of information. But anyway, we're going to do that. Now, when we do filling these orbitals with electrons, we pay attention to the off-bow principle. Have you ever heard of the off-bow principle? AUFBAU? The off-bow principle says to fill the lowest energy orbitals first. And now filling the lowest energy orbital seems easy because you just go in line, but it starts to get more complicated because the gaps, the energy gaps, become smaller and smaller. And so some weird stuff happens. And you got to know this. And unfortunately, they don't show it in the table. So for example, if we're looking at the 100, and then we go to what? We go to the 200, there's a big gap here. And then from the 200, we go to the 21 minus 1, 210, 211. And then from there, we go to the 300, and then the 31 minus 1, 310, 311. And then where do we go? We go to the 32. And the 3-2 are, these are d orbitals, so the 3-2 are pretty effectively shielded. So we go to the 3-2 minus 2, 3-2 minus 1, 3-2-0, 3-2-1, 3-2-2. The 3d orbitals are much more shielded, much less penetrating than the 3p orbitals. And so what happens is s orbitals are the most penetrating, right? And so what happens is this. It turns out the 4s orbitals are more penetrating than the 3d. And so what happens here is the 400 actually goes lower in energy than the 3. Even though the effective distance is much farther, the effective distance for 4 is much, much farther than the effective distance for 3d, right? And so what happens here is this, the ordering of the energies. You guys already know this? Yeah? Or no? What happens is the 4s orbitals are lower in energy than the 3d orbitals. Well, that happens in other circumstances too. And so rather than memorizing these outright, it seems to follow a pattern. And the pattern is very simple. This is the pattern, but it's hard to see this pattern. Because if you look at it, it goes 3s, 3p, 4s, 3d. Well, how do you want to memorize that long line of orbitals? No. What we do is we do this. This is the pattern that we see. And it's easy to memorize. We do 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. What comes after f? 5g, etc. And so we build a little thing like this. And then the easiest way to do this is we go like this. We go, oops, did I do it upside down? I did it upside down, shoot. Well, anyway, we got to figure out a pattern. What is the pattern? It goes diagonal. Which way? Like this?
Yeah.
Like this? I screwed it up because this doesn't work. I screwed up this pattern. Because I'm going, if I go diagonally like this, I go 1s, 2s, 3s, 3p. That's not right. I need to, I screwed up this pattern because I know it's going to go 1s, 2s, 2p. And so I think I think I inverted it. So 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 5g, etc. Okay, now let's see if it works. Yeah, you know, there's a diagonal pattern here. We 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. Do you see that? And so then we get that up there. And this is a heck of a lot easier to remember than that. And so I wouldn't bother remembering this. This is the off-bow principle. Off-bow principle says if you're going to put electrons in orbitals, fill the lowest energy orbitals first, you know, for ground state. Now, that'll give you the lowest energy configuration. And so we filled the lowest energy first, which is the 1s. And so when we fill in the 1s orbital, we put the first electron here. Where would the second electron go? Well, what is this electron? This electron would be called a 100 plus 1/2 electron. The second electron would go, well, off-bow principle says the lowest. But I can't have it the same spin. I have to change the spin. And so this would be a 100 minus 1/2. Okay. And so when we say this, we want to define the electron mathematically. This is the most compact definition of the electron. We need this. This is saying that we have an electron in a 100 orbital and what orientation it is. See that? All right, now the off-bow principle says if we have a third electron, where does it go? The third, well, you would think either the 2s or the 2p, but which one is it going to go to? Is it going to go to the 2s? Now, why does it go to the 2s? Because the 2s is lower in energy. Why is it lower in energy than the 2p? Because it's more penetrating. Good. All right, so we look at this. Now, I could go spin up or spin down. Which one's lower in energy, spin up or spin down? Which one should I go spin up first or spin down first? Which one should I do? Why spin up? Well, the answer is it doesn't matter. They're both the same energy as long as there's no external magnetic field. If there's no external magnetic field, then it doesn't matter if it's spin up or spin down. But then you might argue there is an external magnetic field. The external magnetic field is called the Earth's magnetic field. And so then it makes a difference. If I have an atom in the Earth's magnetic field, then it would make a slight difference in energy, whether I have it oriented with the Earth's magnetic field or against the Earth's magnetic field. If the Earth's magnetic field is like this, then I want to orient it opposite, because the opposites are more stable than... If you put two north poles together, then there's that repulsion. Have you played with magnets? Yeah. And so we want a north pole and a south pole, there's attraction, right? But if we ignore the Earth's magnetic field, then it doesn't matter. If there's no field there, then who cares what direction, you know? It's like, what is pointed up in space? Let's say you're way out in the deep reaches of space. What's up and what's down, you know? It doesn't matter, because if there's no field, no external field, then it doesn't matter. And so it doesn't matter here, because we're going to ignore the Earth's magnetic field, so both are the same energy, whether it's spin up or spin down. All of a sudden, if we put the Earth's magnetic field out here, let's say the Earth's magnetic field is like this, then it matters. If we put the Earth's magnetic field out here like this, then spin down is more stable than spin up. But it turns out that the energy difference between spin up and spin down, because the Earth's magnetic field is extremely weak, is not huge. And so for us, it doesn't matter, but you know, to keep things nice and neat, we might go spin up. Okay. And so that would be the third electron. Now, where would the fourth electron go? This would be like, let's see, this would be hydrogen, helium, beryllium. Where would the fourth electron go? lithium, sorry, lithium, then we do beryllium, fourth electron, it would go in the same off-bound principle. Now we filled it up. Now the fifth electron would go here. Oh man, which one of these three should I do? Is the first one lowest in energy and the last one highest in energy? Or are all the same energy? They're all the same energy, so it doesn't matter which one I pick. And in fact, these are identical. The only difference is the orientation in three-dimensional space. And so these are just orthogonal to each other and identical in energy, so it doesn't matter which one we pick. Any of the three is fine. But once we pick one, then we have to add another electron. We add another electron. Well, you know what? Most people will just pick the first one because it's nice and neat. Now, when we put the next electron in there, should we put it in the same orbital or in a different orbital? We put it in a different orbital. Do you know the reason we put it in a different orbital? Because of electron-electron repulsions. Electrons are negatively charged, right? And so if I put two electrons in one orbital, and then there's some repulsion, because they're both the same charge, so they try to get away from each other. They try to get furthest away from each other. So would furthest away from each other be the 2-1-1 or the 2-1-0? Furthest away from each other. Or does it matter? This is where you have to think in three-dimensional space. It doesn't matter. They're the same. Because furthest away from each other, let's say I have an electron here, they're orthogonal to each other. So one orbital's here, the other orbital's here. It doesn't matter. They're 90 degrees, both of them. And so it's here or here. And so it doesn't matter which one I pick. They're the same. But it does matter that, should I do it spin up or spin down? Now I'm thinking, I should do it spin down because isn't that more favorable? To have it spin down, opposed spins like this. No, you know what I'm going to do? I'm going to do it spin up. It turns out that having parallel spin versus anti-parallel spin is more stable in separate orbitals, like this. Do you know what that's called? Hund's rule. Good. Hund's rule says we fill these orbitals singly with parallel spin. That's going to give us the lowest energy. You just memorize that. And then once we do that, then the next electron will have to pair. There's no getting around that, and we'll have to do opposite spin. Now, we can pinpoint all these electrons because each of these electrons will have a unique quantum number. So for example, what's the quantum number for this electron? 2, 1, -1, -1/2. You see, figuring out the quantum numbers for the electrons is pretty straightforward. Will you say, or not so straightforward? So what I could say is, okay, I have a, let me ask you this. I have a 3, 3, 2, -1/2 electron. Can you pinpoint that? Well, you'd say yeah because you have the 4 quantum numbers, but then you might say no because this orbital doesn't exist. This would be called a 3f orbital. Are 3f orbitals in existence? Do you see a 3-3? No, there's no such thing as a 3f orbital, so I can't do that. I could have done something like this. I could have done a 3, 2, 2 -1/2. That orbital exists. Where is that electron? Let's say I'm going to excite an electron to 3, 2, 2 -1/2. Where did it go? It went into this orbital with spin down. So that's right here. So this is the quantum number, so it'll tell us that. And so I might excite an electron. Boom, I excite an electron out there. All right, so we have off-bow principle. We have the Pauli exclusion principle. We have Hund's rule. And there are different ways of representing this. This is the least informative. The what we call electron configuration. This is the least informative. This is the most informative. This is the most informative because we can see the gaps here between the orbital energies. We lay it all out. This is the most informative, but the problem is this takes up a lot of space. So if we want to condense this down, we're going to lose some information. Here we lose a lot of information because we don't see the spins, we don't see the individual orbitals. For example, we don't see the 3 2p orbitals. Both those electrons can't be in the same p orbital. Sometimes, okay, we'll break it up. Both these electrons can't be in the same, so we'll make one px, the other py, or py and pz, or px and pz, doesn't matter, and put those separately. And we get a little bit more information, but we don't see the spin. And so we go to this one, the orbital box diagram. The orbital box diagram has more information, but it's lacking the gaps here. We don't see the gaps. And so we go from the least informative to a little bit more informative to a little bit more informative to the maximum. This is the maximum. What do we call this? Okay, this is the electron configuration, condensed. This is electron configuration expanded. This is the electron box or orbital diagram. This is called the energy level diagram. The energy level diagram you should be able to draw, even though Petrucci doesn't. Petrucci doesn't do this because it would take up too much space and the book would get longer, even longer. Now it's already over 1,000 pages, right? And so Petrucci doesn't do it because, and the homework, they don't do it either because otherwise it takes up too much space. But I want you to do it because it's the most informative and that'll tell me if you know it well or not. Well, anyway, the Aufbau process is just filling the lowest energy to higher energy. So it's just this consecutive thing. Aufbau. What fills first, the 4s or the 3d? According to the Aufbau principle, 4s fills before the 3d. And so let's take a look at filling these. So I'm going to go up to scandium. Look at scandium. Why did they write the 3D first? Look at this. Are you familiar with this? Argon. You know what argon stands for? The argon core, followed by 3D1 force 2. That's often done. You have two choices, and I'll talk about this in just a second here. Well, let's continue filling this up. So this is oxygen, fluorine, neon. Neon has the filled shell. This is what we call the first shell. And so the first shell is filled. When we fill the first shell, that's helium, the helium shell. If we fill the first and the second shell, we call that, the second shell, we're going to call that neon. The neon core, fill that. And then once we go to neon, we'll continue until we fill the third. Okay, now this shell is kind of different, right? Because this shell is missing one of the sublevels, the 3D. So this would be the third shell. This shell is going to look different than in the hydrogen atom because the third shell in the hydrogen atom would include the 3D. But what we're doing is we're just including the orbitals with close energies here. But it gets a little bit tricky because in terms of distance, it's different. And so the third shell is filled. This would be what we call argon. And then the fourth shell. The fourth shell is going to include the 4 Ps, which I'll write here. The 4 Ps are higher in energy than the 3Ds. And so this is going to be 4, 1, minus 1, 4, 1, 0, 4, 1, 1. Okay, so we filled the first, second, and third shell. That's what we call argon. And so what we're going to do is we're going to start looking at the fourth shell, which they're doing over here. And so starting off in the fourth shell, We can see that here. Actually, we might as well just see it over here on the periodic table. You can see this. The first row of the periodic table is the first shell. The second row is the second shell. Third shell. The fourth shell is here. Fourth shell in the periodic table. Starts off with potassium, calcium, scandium. So let's go ahead there. So filling up the fourth shell, we have potassium. It's after potassium. Calcium. Scandium. Scandium, we throw an electron into 3D. Scandium and then yttrium, right? Or no, titanium, sorry. Scandium, titanium, and then vanadium, and then, well, that's what we got here. Let's stop here and let's take a look. Vanadium, we have argon, 4s2, 3d3. So we got argon, 4s2, 2 electrons, and 3d3. You see that? After vanadium comes chromium. But something funny happens with chromium. Chromium should be this. Chromium should be, we fill up all the way to here, which is the same as argon. We get 4s2, 3d4. And so chromium should be argon, 4s2, 3d4. But why did they write this like this? 4 argon, 3d4, 4s2. Now, the way I use shells are very tricky in terms of visualizing. When you look at this, this is the filling order. This is by shell, but this is a different way of looking at the shell. This is by shell in terms of valence shell versus core shells. Do you know the definition of the valence electron? The valence electron is defined as the outermost electron. What is the outermost electron here? Is the outermost electron the 3D? It certainly is in terms of energy. Or is the outermost electron the 4s? Which one is the outermost electron? The 3D or the 4s? The 4s is the outermost electron. Why? Because its effective distance is farther. But if the effective distance is farther for 4s, why isn't it higher in energy than the 3D? Because the 4s is more penetrating. And so this is the weird thing that happens. If you're an oxidizer, let's say I'm an oxidizing agent, I'm going to come and pluck an electron. Am I going to come and pluck an electron, the 3D, which should be easier to pluck off? Because it's higher in energy? Or am I going to come and pluck off a 4s because it's closer to me? See, in other words, if you're an oxidizer, are you going to dig in for a 3D electron and pluck that off? Or are you going to just take the 4s, which is going to have a higher or farther effective distance? Somebody keeps calling me. What are you going to do? Well, this is what we do. If you're an oxidizer, you pluck the electron that's closest to you. You know, even though, if you're an oxidizer, do you discriminate? Do oxidizers have brains? And they go, wow, you know, there's a delicious apple, but it's a little higher in the tree versus the apple right here. Do oxidizers have brains and go, wow, I better get that better apple there? make an effort and bypass this closer apple. What do you think an oxidizer is going to do? It's going to try to take any electron, whatever. If it can't pull this one close, then it's going to try to get the next one, which might be there, which would be easier to pull off, maybe, right? And so the oxidizer is just going to be indiscriminate, and so it's going to attack the first thing it sees. If it attacks the first thing it sees, it's going to see the 4s or the 3d. It's going to attack the 4s. Even though, hey, it's more profitable to attack the 3d, it's going to cost you less energy. Does the oxidizer care? Does it have a brain and it thinks that way? No. And so it's indiscriminate. If it can't, then it'll go for, if it can't pull off the 4s because of the energy, then it'll take a 3d, right? But it'll pull off the energy difference between 3d and 4s is extremely small. And so what we call these, the 3d, we call core. We call it core even though it seems like it's the outer shell, doesn't it? But the 3d we call core because its effective distance is very close to the nucleus. And so actually the 3d are inner electrons, inner shell electrons. So when we're talking about valence shells, the valence shell will include the 3d. When we're just talking about shells like the periodic table, it doesn't. And so we call that core, we call this valence. And so oftentimes the electron configurations are shown to show the valence electrons out here. The valence electrons are defined as electrons in the highest n level because the highest n level will be the ones that are furthest from the nucleus. Now, what's going to happen here is this. There isn't a huge energy gap between these. And so what happens is symmetry. I talked about symmetry before. And symmetry is like this. Symmetry, think about this. Let's take a cake and cut it in half like this. It's going to be weird because I'm going to cut it down the middle like this. So I have two even halves like this. And then let's take a slice out of that. Like this. So what I am, when I look at this is what I see. I see the 3D. 3D can hold a total of 10 electrons. But I see this is one electron short from being half filled. So one electron short from being half filled is like this. This whole thing's empty here. And so I'm just one slice. Otherwise, it'd be nice and symmetric. I'd have a whole half cake rather than this. Well, it turns out that I have an electron over here. This electron over here is paired. There's a pairing energy. So there's a little bit of repulsion. And so what I can do is I can promote this electron over here. If I promote an electron over here, then what I'll do is I'll fill this cake up. I'll fill the remaining slice. And so this will be a nice half-filled subshell. And so it's got that symmetry. And in this case, it's more stable. So what we come up with is this. Half-filled d orbitals have some stability. And so it depends on the cost. In this case, this is what happens. And this is observed in nature. When we get to chromium, one of the s electrons gets bumped up into the d to complete the symmetry. Here. Okay, when we get to manganese, then we don't have to bump an electron. For manganese, it's already naturally half filled. And so we can keep this as fully filled. And so up here we'll have a half-filled S and a half-filled D. And then things progress. Iron, we add another electron. Cobalt, another electron. Nickel, another electron. However, when we get to copper, we run into the same thing. When we run into copper, we have this situation where the electron configuration is argon 3, actually, let me do it. My 4s2 3d9. Or argon 3d9 4s2. Now, if you think about D9, when I think about D9, this is what I think. I have a nice cake like this. And this nice cake is going to have one slice missing out of it. And so, but I can get that one slice if I just take it from the s orbital. And so if I do that, if I take one electron from the s orbital and promote it here, then I can fill the cake. And it turns out that this is what happens. Filled shells are symmetric. So if I fill this shell, then what I have is spherical symmetry. One s orbital is full. Even a half-filled 1s is spherically symmetric, so it doesn't matter. When I get to the p's, if I have partially filled p's, it's going to be asymmetric. But if I fill all 3 p orbitals, then it's what we call spherically symmetric, because px, py, pz, spherically symmetric. And so this is a spherical distribution of electrons. And the same thing here. Half filled is going to be spherically symmetric. And completely filled will be spherically symmetric. And so what I can do is I can completely fill the D subshell, and a filled D subshell is stable. Filled D subshell is stable. It's stable. And so when I go here, that's what happens with copper. Copper, we promote an electron and we can fill the D subshell. But let's go back to nickel. If I look at nickel, nickel's 2 electrons short. So why don't I promote both those electrons and fill the D subshell in nickel? I can promote these 2 and fill it. Why doesn't that happen? Why that doesn't happen is it costs energy to promote those 2 electrons. And so in this case, it's not beneficial, because if we have to promote 2 electrons to fill that, in terms of energy, there's not enough return. And so it's okay to promote 1 electron, but not 2 electrons. And so this is what we see in the elements here. We see this pattern repeat. The first one was chromium. Molybdenum, tungsten shows a similar pattern. But it becomes less significant, because when you get to the higher energy orbitals, it becomes less significant. Copper, silver show the same pattern. So what's a common charge for copper? Well, one charge is copper plus 1. Copper plus 1 is we lose this electron here. Another charge is copper plus 2. But if we go to copper plus 2, it breaks the symmetry here. Now, with copper is very unusual. We have to look at it in Chem 1b. In Chem 1b, when we look at copper, it makes sense why it does this. But in Chem 1a, I don't want to talk about it now, but I'll talk about zinc. What's the most common charge for zinc? In fact, there's only one charge for zinc. What is it? Plus 2. Plus 2 is a common charge for zinc. In fact, what's a common charge for most transition metals? A common charge for most transition metals is plus 2. Plus 2 because we have 2 valence electrons, and then we might start attacking some core electrons. Here, for iron, we can attack core electrons. So plus 2 is common. We lose those 4s electrons. And then plus 3 is common. We lose one of these. But we can lose one of these easily because one of these is paired, and that leaves us with half. Right, so plus 3. Zinc, only plus 2, because in order to go to plus 3, we have to break a filled subshell, the D. And so basically, the reason I say that quantum mechanics is the theory underlying chemistry is because, look, the periodic table is based on quantum mechanics. We have the s orbitals here, the d orbitals here, the p, the f. And then we have higher energy excited states. These are all for ground state. And so we can figure out the electron configurations for the elements based on where it is in the periodic table. Where it is in the periodic table is going to tell us the order of the orbitals. And so let's go to europium, element 63. What's the electron configuration for this? Well, element number 63, actually maybe I'll do it on this one here. Element number 63 is here. And so we could do the core, like we could xenon core is 54 electrons. So those 54 electrons takes us here. And then we go to 55. So it would be xenon 6s1, 6s2. 6s2. That takes us to 56. And then do you see this? 57 through 71 goes down here. So we go 6s1, 6s2, 4f1, 4f2, 4f3, 4f4, 4f5, 4f6, 4f7. And then we're done. That takes us to 63. Or we might go to element number 92, uranium. If we go to uranium, what's the electron configuration for that? So we backtrack. We go to radon, 86. So we do radon, and then we go to 87, 7s1, 7s2. And then we look at 89. 89's down here. And so it would be a 5f1, 5f2, 5f3, 5f4. That would be the electron configuration. But what if we did element number 104? How would we do that? We do element number 104 here, which is RF. It's RF. RF. Actually, I don't know. Well, we go to radon, 7s1, 7s2, and then we got to drop down here, 5f, 14, and then we go back up here. We go from 103 to 104, which would take us to D, 6D, 61, 62, 61. We'd stop there. Does that make sense? Okay. And so we use the periodic table. The periodic table is based on the orbital. And just a little bit more. Chapter 9 is just a continuation of Chapter 8. Those are atoms. The periodic table, Mendeleev. Mendeleev came up with one of the first periodic tables, actually, one of the first usable. This is a periodic table from Mendeleev. The periodic table, did Mendeleev develop quantum mechanics? He must have developed quantum mechanics if he did the periodic table, did he? The periodic table is based on quantum mechanics, isn't it? Actually, no. Mendeleev. This is Mendeleev's periodic table from 1871. Was quantum mechanics around in 1871? No, the quantum mechanics came around the 1900s, mid-1900s, right? And so, how did Mendeleev develop the periodic table without quantum mechanics? Right, from properties. And so, developed the periodic table based on periodic properties. So we could see the periodic properties here. Periodic properties, when we look at it, this is atomic volume and atomic numbers. We can see easily the patterns here. And so Mendeleev can base the periodic table on atomic volume. The volume increases the atom as we go across. As we go across a row, the rows are called periods, the volume increases. Then as we go down the column, the volume increases as well. Because going down a column would be lithium, and then sodium, potassium, rubidium, cesium. You can see the volume increases as we go down, and the volume increases as we go across the periodic table. Although there's some little gaps and flat parts to this. We'll look at it later. And so basically he did it based on properties. He predicted a new element right below silicon called it Eka silicon, which is named germanium. X-ray emission. We'll skip this. This, this is the X-ray spectrum. This is not the visible spectrum, but the X-ray spectrum, we see the same kind of deal. In the X-ray spectrum, we use these as fingerprints. So you can tell what element you have based on the X-ray spectrum. In fact, when they sent a probe to the moon to analyze the rocks there, they figured out the elemental composition of the rocks by shooting X-rays at it and measuring the X-ray spectrum. Using X-ray, this is called X-ray photoelectron spectroscopy. But you can see, you can easily tell brass. Does brass have copper in it? Can you see? Yeah, brass has copper. Copper has these two lines. Do you see these two lines in brass? What else does brass have? Brass is a mixture. Brass has these two lines here. What are those two lines? Oops. Do we see it? I don't see it. So we got to keep looking. And so we can see. So each of these are unique, identified, because the energies of the orbitals change and the transitions change, and therefore we could use these to identify or uniquely identify certain elements. That was the long form of the periodic table. We divide this into metals, nonmetals, and metalloids. The metals of this color. The nonmetals are over here, and the metalloids are these green ones here. And so the metals, they all have similar properties. Metals are reducers, they give up electrons. Nonmetals are typically oxidizers, they take electrons, unless you're a noble gas. If you're a noble gas, right, you're stable. And so we identify metals based on their properties. Metals all are good conductors of heat and electricity. Metals are malleable and ductile. Metals have moderate to high melting points. Metals are chemically reducing agents. And then we have nonmetals. And then we have the metalloids, which have properties between them. Nonmetals, the properties of nonmetals vary much more. And so you have some nonmetals like helium, which are totally unreactive, and you have some nonmetals like fluorine, which are incredibly reactive. And so nonmetals are a little less consistent as far as properties go. But if it isn't a metal, then it's a nonmetal or metalloid. Metals tend to lose electrons. And so the further you go left, they tend to lose electrons, so they become isoelectronic with the nearest noble gas. So for example, lithium, if lithium loses one electron, it'll have the same electron configuration as helium. Beryllium, 2 electrons. Aluminum, 3 electrons. Tin, 4 electrons. And so we're becoming isoelectronic with noble gases. Metals tend to lose electrons. Nonmetals tend to gain electrons. Then we have electron configurations of ions. These have the noble gas electron configurations, lithium plus, sodium plus. Lithium plus like helium, sodium plus like neon, potassium plus like argon. These are also noble gas electron configurations, as well as aluminum. And then we have pseudo-noble gas configurations, like silver. Why do they call silver a pseudo-noble gas configuration? Well, let's take a look at the electron configuration for silver. Yeah. And I'll do that. The electron configuration for silver, well, if I look at silver, silver is not going to be argon. Silver, let's go ahead and tell me. Why don't you tell me the electron configuration for silver? It's not going to be argon. We're going to use krypton. So start out krypton and tell me the electron configuration for silver. Krypton, then what? 5s2. 5s2. 4d. 4d9. Look at the D and tell me what you notice about D. D is 1 electron short from being a full cake, right, or full pie. So that symmetry is important. So what happens is, this is not the actual electron configuration. What happens is we can promote 1 electron, not 2 electrons, but 1 electron. 2 electrons would cost too much energy. So we promote 1 electron, and silver should be krypton And I'm going to rewrite it 4d10 because now that's 5s1. So how many valence electrons does krypton? I mean, how many valence electrons does silver have? 1. And so if we go from silver to silver ion, Ag+, then the electron configuration is going to be krypton 4d10. Krypton 4d10, this is called pseudo Nobel gas. It's called pseudo Nobel gas. Well, it's got Nobel gas. This is filled core. But this filled d subshell is also stable. And therefore, this is pseudo Nobel gas, even though it's not technically the same electron configuration as Nobel gas. And so silver is like that. Well, what's under silver? Gold. And zinc, too. You know, we talked about zinc just a minute ago. This is pseudo Nobel gas. These are the 18 plus 2 rules. Lead. Lead. The 18 plus 2, what are the common charges for lead? Well, let's take a look at lead really quick. What's the electron configuration for lead? Well, I go here. For lead, I go xenon. And then I'll go xenon, and then what? 1, 2, 3, 4, 5, 6. 6s2. And so take it from there. We'll go xenon, 6s2, and what comes next?
Four.
4f14, and then what? 5d 10, 6p 2. Now what I do is we'll rearrange this, or this. We'll arrange it in order of distance from the nucleus. So 4f will be the closest, so it'll be 4f14. And then 5d will be the next closest. And then the 6s2 and the 6p2. Now what do you think the common charges for lead are? The common charges for lead are going to be, if I lose the p electrons, I get lead plus 2. If I lose the p electrons and the s electrons, I get lead plus 4. What are the common charges for lead? Plus 2 and plus 4. And so this would be the pseudo 18 plus 2. Or not pseudo 18 plus 2, but 18. And so we could read this. There's a little footnote there. 18 plus 2. Where does that come from? In the configuration labeled 18 plus 2, all outer shell electrons except the 2s electrons are lost, producing an ion with 18 electrons in the next to outermost shell and 2 electrons in the outermost. So for example, tin 2 plus. And so what that is, all that's saying is that for lead, we can lose, these 2, and then we'll get plus 2, or we can lose all 4 and get plus 4. There's actual numbers there, but we don't have to calculate them. You can see what it's going to be just by looking at the electron configuration. Then we're going to have others that don't obey any of the rules, like iron 3. Iron 3, we have to remove both the 4s and one of the 3 ds. Iron 2 we could have seen. Iron 2 is got 2 valence electrons. We lose that. Chromium 2 is 2 valence electrons. Cobalt 2 is 2 valence electrons. And so a lot of these we could have just recognized. Just change that. So this is the electron configuration for iron. Now for anions, anions and nonmetals. Nonmetals tend to gain electrons until they're isoelectronic with the nearest noble gas. So oxygen wants 2 electrons, fluorine wants 1 electron, nitrogen wants 3 electrons. And so that's something you guys are familiar with, correct? Yeah. And so we can see it here. Iron has 2 valence electrons. So iron 2 plus is no problem. We lose those 2 valence electrons. Iron 3 plus, now we've got to take a core. So we're going to take one of the D cores. We could try to get it for iron 4 plus, which means removing another D, but it becomes increasingly difficult. So +2 is very common. +3, okay. +4, less common. Hydrogen can either lose or gain one. And so hydrogen's in two groups, you know. Because if hydrogen loses one, then it forms H+. But if hydrogen gains one, it'll be isoelectronic with helium. And so hydrogen can gain or lose an electron. So if it gains electrons, then it's like fluorine, chlorine, bromine, iodine. All these gain one electron, just like hydrogen. Over here, hydrogen loses one electron, just like lithium, sodium, potassium, rubidium. And so hydrogen has interesting properties. It can gain or it can lose. It generally loses, so in most cases, hydrogen is a reducing agent. Sometimes it will gain and be an oxidizing agent. And so most of the time it's placed in group 1, not in 17. Now, the size of the atoms is very tricky, like we said, because is there a hard shell on an atom? There isn't, so how do we measure the size of the atoms? The size of the atoms is the atomic radius. And there are going to be different radii. For example, the covalent radius is based on looking at a bond and cutting it in half. And so if I have a hydrogen molecule, the size of the atom is not really fixed, right? But if I have a hydrogen molecule, then I can do this. I can look at the bond distance. Now, what about the Heisenberg uncertainty principle and nuclei? It turns out the nucleus is very massive compared to an electron. And so pinpointing nuclei is no problem. So we can pinpoint the nucleus here, we can pinpoint the nucleus here, and we can measure the distance. And so we aren't going to be impacted by the Heisenberg uncertainty principle. We can measure this distance. When we measure the distance between two hydrogen atoms, this is HH, and then cut that in half, that's what we call the covalent radius. So the covalent radius would be half the distance here between the two H atoms, like this. And so just cut that. And so this would be the radius of the hydrogen atom. So that's the covalent radius. The ionic radius is based on the distance between the nuclei of ions joined by an ionic bond. Okay. The metallic radius is 1/2 the distance between the nuclei of two atoms in contact with a crystalline solid metal. The van der Waals radius is similar to the metallic radius, except it's for solid samples of noble gases. The problem with measuring the radius is if you stick a probe in here, you're going to hit empty space mostly, right? And so if you stick a probe here, they say this is like trying to measure the diameter of a rotten grapefruit with a needle. You know, the needle is just going to go right into the grapefruit. Well, the same thing here. If you put a needle here, empty space, what you feel is a voltage. You know? And so, you know, where do you stop? At what point? Because you can force your way very close to the nucleus. No hard surface. So these are the ways we determine the radius. Here's the covalent radius is at the top, metallic radius, and ionic radius. And so you get 3 different radii for sodium. Sodium in the molecule like this, Na2, which is very unusual, is 157 picometers. Sodium in the metal, solid, is 186 picometers. And sodium as an ion is 99 picometers. And so this is very interesting because, you know, these are just neutral sodium atoms, either in the molecule or the metal. But the radius is quite a bit different. And the radius is going to be dictated by, you know, the bonding interaction. How strong that bonding interaction is. Well, what we do is we'll just average out the radii, you know, the covalent radii, the metallic radii, and come up with some kind of average radius. And so we can see these are some kind of average radius of the atoms here. And what we can see is that the size, you know, lithium is a lot bigger than fluorine. And so as we go from lithium to fluorine, the size shrinks. So as we go across a period, the size shrinks. But as we jump down, lithium to sodium, sodium's bigger, as I mentioned before. Then we go to potassium. Potassium is big, and then it gets smaller. And so the question is number one, why does the radius go and get smaller as we go across a period? I'm going to stop pretty soon. I'll just talk about size and then we'll stop. Actually, I'll just talk about it here. As we go across the periodic table like this, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Lithium is big. Fluorine is small. Hard to see there. Let's show you a better figure. Here. So lithium's big, fluorine's small. What makes fluorine smaller? Fluorine's got more protons, it's got more electrons, it's got more neutrons. So it's got more of everything. Why is it smaller? Shouldn't it be bigger? Shouldn't fluorine be a lot bigger than lithium? No, it's just the opposite. Well, that doesn't seem to make sense. Well, let's go to lithium and sodium. Sodium's got more of everything. It's got more protons, more neutrons, more electrons, and it's bigger. So sodium is bigger than lithium. It's got more stuff. But fluorine is smaller than lithium, and it's still got more stuff. And so why is that? Do you guys already know this or no? Why that is because of... I'll tell you why that is. It's because of... screening and penetration. Or, in other words, shielding and penetration. Didn't we see shielding and penetration before? Well, we see it again now. And this is the reason why what we have to do is we have to get deeper into shielding. And we have to understand it deeper. This is not in the book, in the chapter. This is in the homework, though. It's John C. Slater. John C. Slater came up with something called Slater's rules. They aren't laws because it's not too terribly. These are just estimates. This is estimates. He didn't call them law. It's just a rule. A rule. The difference between a rule and a law is rules can have a lot more exceptions. The equation isn't going to be as consistent. So this is Slater's rules. This is number 69. We have seen that the wave functions of hydrogen-like atoms contains a nuclear charge Z for hydrogen-like atoms and ions, but modified through equation 9.3 to account for the phenomena of shielding or screening. Shielding and screening, we got to think of in terms of penetration. In 1930, John C. Slater devised the following set of empirical rules to calculate a shielding constant for a designated electron in the orbital ns or np. And so this is what Slater's rule does. Slater's rule estimates what the Z is going to be. And so if you're the outermost electron, what is the Z that you're going to experience? If there are no electrons between Z and U, then you see Z, the full charge. But what happens if there are all of a sudden there are electrons here? If there's an electron here, are you going to see the full Z? No. If there's an electron here, what you see is something called Z effective. Z effective is going to be less than the full charge here, right? And so it depends on where this electron is. If the electron's here, then this electron's going to block it out. So let's say Z is plus 10. If you have a Z of plus 10, and there's an electron here blocking your view of this, you know what your Z effective is going to be? Plus, not plus 10, it's going to be plus 9. Well, let's say I'm going to throw in another electron right there. What's your Z effective going to be? Plus 8. Another electron here, it's going to be plus 7. What if I throw an electron here? Is this electron out here going to drop it again? Now I'm at plus 7. I throw an electron here, am I plus 6 now? No, I'm not, because this electron isn't as effective as these. And so Slater said this. Slater said inner shell electrons effectively shield. Same shell electrons are poor shielders. And so what Slater did was he just came up with numbers for this. They're just very simple numbers, but these numbers are helpful for us to visualize these things. And so what Slater said is this. Slater devised the following set of empirical rules to calculate a shielding constant. Write the electron configuration of the element. So we write out the electron configuration, but we write it like this, where we put the 2s and the 2p in the same shell. 2s and 2p are in the same shell. Electrons in groups to the right contribute nothing. So if I have an electron out here, is that going to shield anything for this electron? No, it doesn't shield. So that's what Slater means by this. Electrons to the right don't shield anything. All the other electrons shield. Okay, if it's in the same group, then like this. If it's in the same shell, we have to deduct minus 0.35. So this electron is, okay, these three we'll deduct. So these 3 electrons takes us to plus 7. And this electron in the same shell will take us to plus 6.65. You get that? Because it's in the same shell. And so let me just rephrase that. Same shell electrons, that is, if it's in the same N, shield to the extent of 0.35. Electrons in the inner shell, that is the N-1 shell, inner shells, the first inner shell shields to 0.85. I mean, so this first inner shell here, so let's say this is N equals 3. So if this is an N equals 3 electron, I deduct 0.35. If this is an N equals 2 electron, then I deduct 0.85. If this is an N equals 1 electron, that would be the N-2 shell. If I go to the N-2 shell, how much do I deduct? I deduct a full 1. And so in this shell, I get -1. And so if I'm at plus 10, I got 3 here, that's going to take me to plus 7. I got 2 here, that takes me to plus whatever. And I got 1 here. Does that make sense? So Slater devised these rules to estimate what the Z effective, the charge, is going to be. But what we're going to do is we're going to condense this down because this is too much detail for us. What we're going to say is this. We're going to say that same shell electrons are poor shielders. Inner shell electrons are very effective shielders. Inner shell being, if I'm in the N equals 3, then anything in the N equals 3 will be same shell. Anything in the N equals 1 or N equals 2 will be in the inner shell. And so inner shell electrons are effective shielders. So if you want some practice, you can use Slater's rule to calculate Z effectives for copper, 3D electron, for copper 4s electron, for valence electron in oxygen, etc. And hence, this is why the size decreases as we go across the periodic table. So let's look at lithium to beryllium. Lithium has a Z of +3, right? Z of +3. And then how many electrons does lithium have? Lithium has 3 electrons. Okay, then we go to beryllium. Beryllium has a Z of +4. But then you go, it has 4 electrons. Right? But we have to look at where those electrons are. And so what happens here is we get +1 proton, +1. Now we got to think, +1 same shell electron or +1 inner. And so we go from here. We go from helium 2s1 to helium 2s2. That second electron we just added is in the same orbital. Is an electron in the same orbital an effective shielder or a poor shielder? Same shell electrons are poor shielder. So essentially what beryllium sees is beryllium sees an increase in Z that's pretty much unshielded because that electron is in the same shell. Does that make sense? And so what happens here is beryllium is going to see a higher Z effective. Z effective increases, that means lithium might be this big and beryllium is going to shrink down. And then let's go to, after beryllium, we go to boron. When we go to boron, we add another proton, so +1 proton, but at the same time, we add another electron, plus an electron. Is the electron we're adding an effective shielder? No, because the electron that we're adding is this. It's going to be helium 2s2 2p1. So that extra electron that we're adding is in the same shell. Same shell electrons are poor shielders. And so essentially what boron's going to see is it's going to see a higher Z. And so it's going to shrink down smaller. And so the reason why atoms shrink as we go across is because Z effective increases, we're adding protons, but at the same time we're adding electrons, but those electrons are poor shielders. And therefore, they don't shield very well. But that's the case here. That's the case here. But what happens here? We add a proton, shrinks. Add a proton, shrinks. Add a proton, shrinks. Add a proton, shrinks. All at the same time we're adding electrons, but those electrons are poor shielders. And then we get here. Take a look what happens here. This is flat line almost. In fact, it is flat line. If I blew this up, there's flat line. The flat line occurs here. The transition metals are all about the same size. Why is that? Well, the transition metal is kind of flat line here because of this. I add a proton. So let's take a look at a transition metal. I'm going to take iron and nickel. Iron and nickel are about the same radius. Actually, let's look. Or maybe iron. Let's get something. Well, let's just do iron and cobalt. How about that? Iron and cobalt. I don't know if you guys can read this. Iron is 126, cobalt is 125. They're about the same size. Do you see that? Why is that? Why didn't it shrink? Because if I do iron to cobalt, I do +1 proton. But I also do +1 electron. And I have to see, so I got one more proton, shouldn't it shrink? And so if I look at iron, iron is argon 4s2, 3d. 1, 2, 3, 4, 5, 6, 3d6. I should rewrite this. I'll end with this. It wasn't meant. I need to talk for so long. Argon, 3d6, 4s2. Now I go to cobalt. Cobalt is one more proton, but it also has one more electron. And so it's going to be 3d7, 4s2. Where did that one more electron go? Did it go in the same shell? The outermost shell? The outermost shell is going to dictate the size. Did the extra electron go on the same shell or no? See, what I did here was I did +1 proton, and for lithium, beryllium, whatever, those are all same shell. But this is +1 electron, inner shell. It's an inner shell electron because it's a 3d. 3d electrons are inner, 4s are outer. Does that make sense? And so inner shell electrons are effective shielders. And so I add one proton, but that additional proton's canceled out because I added also an inner shell electron. And therefore, when I look at iron, iron's 126 picometers, cobalt's 125 picometers. Essentially, no change. That's what happened. Whereas when I look at lithium, lithium is 155, beryllium's 112, a dramatic shrink. So here I added one proton, but I also added one same shell electron. Same shell electron does not cancel out, right? Effectively, the Z. So do you guys got that? All right, now the size jumps. So if I go lithium to sodium, the size jumps because I'm adding shells. And so sodium has more shells of electrons, so it's got to be bigger, potassium, rubidium. And so the reason size increases this way is because we're adding more shells of electrons. And so the net result is this. The net result is size decreases going up and right. So size decreases this way. Smallest atom is what? Is the smallest atom hydrogen or is the smallest atom helium? You tell me. Is the smallest atom hydrogen or is the smallest atom helium? It's got to be hydrogen, right? Hydrogen is only one proton, one electron, but helium is 2 protons, 2 electrons, so it's going to be hydrogen, right? Right? Or wrong? Helium's smaller than hydrogen. Why? Because I add a proton and I'm adding a same shell electron. Same shell electron is not effective at shielding, so that proton, that additional proton is going to pull in the electrons even closer. Does that make sense? Z effective is going to be greater. Well, I'm going to stop here at atomic radius. And